So in this video, we're going to look at a method of solving for the internal forces in members using the method of sections. So we have a somewhat larger truss. It has a periodic geometry to it, and that each panel of the truss is 10 feet wide. There are 1, 2, 3, 4 panels, so it's 10 feet wide in total, and its height is 7.5 feet. It has a loading at joint D and joint F that is equal. The magnitude is 37 kips in both cases, and it's in the downward direction. And we want to find the force in members DF and DG. So I've highlighted those in red, and you notice that if I were to pass a section through those two members, it would also naturally pass through EG. So taking the approach of using method of sections here, we would get the actual force in member EG for free as well. So just like method of joints, the first thing that you want to do when you're attempting to solve a problem using method of sections is to determine the external reactions. And those are going to be at point A and point H. You probably see that it's going to be easier once you pass your section and break the truss into two to use the right-hand section of the truss. So really the only reaction you need is the vertical reaction at Y. So if you were really in a rush on a time test, one thing you could do is just sum all moments about A when treating the entire truss as a rigid body in equilibrium, and that would allow you to isolate the quantity HY. So hopefully everyone sees we will determine all three reactions individually. It's a story we've told quite a bit. When trusses are loaded the normal way, perpendicular to their span, all of your horizontal reactions don't have to do anything. So AX in this case is 0, since the sum of all forces in the X direction is 0. If we want to determine the vertical reaction at H, all that we need to do is sum all moments about point A. That will isolate or remove the effect of AY, since the moment of AY about A will be 0, since that force acts directly upon that point. HY is a vertical force. If we determine the perpendicular distance from point A to the line of action of HY, it's just going to be the entire span of the truss, which is 40 feet long. Notice if you pin an A and you push up in the HY direction, that will induce a counterclockwise rotation. So the sign convention of that moment will be positive. So I have positive 40 HY. In contrast, when both external forces P act in the downward direction, they're going to induce a clockwise rotation. So they get a negative sign for both of those. Relative to point A, the first force is 20 feet away, and the second force is an additional 10 feet away, so its perpendicular distance is in total 30. That's how I'm getting the minus 20p, the minus 30p. If you want algebraically, you can combine those into like terms and get minus 50p plus 40hy equals 0, which solving for hy will give you, depending on which value you're given for p, I was given 37 kips, that will be 46.25 kips for hy. Then if you wanted to, you could go ahead and solve for the unknown vertical reaction at AY by summing all forces in the y direction. And basically what this equation says is that the vertical reaction that AY has to provide is whatever portion of the external loading to P that HY hasn't already compensated for. So that turns out to be 27.75 kips. We already showed how to pass a section through the two members of interest. We could then analyze using rigid body equilibrium, either the right side or the left side. I think the left side is a little bit easier. Remember, whenever you pass a section, basically you have to replace the effect of breaking that truss apart by drawing the actual internal forces in those members. And the technique that I showed you how to do in the first portion of the Chapter 6 lecture is to have all of the forces associated with members that you segment pulling away from the pins. And remember, if the member is pulling the pin in this way, by Newton's third law, the pin is pulling the member back. And that's what I'm actually showing here. If the member is pulling the pin to the left, then the pin is pulling the member back to the right. And if that member is in equilibrium, which hopefully this truss is, the sum of all forces here must be 0. So this is a two-force member. So by Newton's second law, you must have an equal and opposite force on the left side. So if you notice that member is being pulled apart. So whenever you do methods of sections and you assume that the internal forces pull away from the pin, that's naturally an assumption that the member is in tension. So if the number turns out to be positive, that is going to be a tension-based member. So how can you actually go about solving for all of the unknown forces in the two that you want, at least, FD and FGD? Well, if you notice, you have two unknowns acting at point G. So if you begin by summing all moments about point G, that will allow you to isolate force FD. If you think about the truss there, and we're pinning here at point E, and we pull in that direction, that is going to be a counterclockwise rotation. That's how I got the positive sense for the 7.5 FD. The perpendicular distance, that's a horizontal force. So the perpendicular distance is just the vertical distance from point G to point F, which is 7.5. So that's 7.5 FFD for the rotation that this force exerts about that point. In a similar fashion for the, we know that HY actually goes in the vertical direction. So if you pin at G, it's also going to induce a counterclockwise rotation. If you extend that line of action, you notice that the perpendicular distance is going to be the horizontal displacement from G to that vertical line, which is 10 feet. That's how I'm getting the 10 there. They are both positive in the way we've shown on our free body diagram, and the math is showing us here that that must mean that the one we don't know, FFD, actually turns out to be negative. So when you do the computation for my value of HY, I got 61.67 kips. It is negative. Since by convention and method of sections, when you assume that the members are going away from the joints, that's a tension assumption. When you get a negative value, that means that it is in a compression. So you just want to kind of follow that approach. I actually showed you how to do one more here. How do you actually determine the unknown reaction in member GD, FGD? Well, if you notice, it is the only member that has a vertical component. These both are purely in the horizontal direction. So as long as you can express the vertical component of FGD in terms of the unknown magnitude, which you can, because you know its geometry acts along the actual orientation of that member, you'll be able to isolate this and solve for it just by summing all forces in the y direction. The one thing to be careful of is how you actually do your decomposition of FGD. Again, we need to look at the geometry of the truss, and since this line of action of this force is going to follow a right triangle where the width is 10 feet and the height is 7.5, just like we did in the last problem, you can use Pythagorean's theorem, find that the hypotenuse of that triangle would be 12.5. Then if you notice here, if you wanted to get the y component, it's going to be related to the sine of that angle, which would be opposite divided by hypotenuse. That's how I got the 7.5 divided by 12.5. That is the sine of this angle. I should have noted here that this is actually going to the, in terms of the y component, I should say, it is going positive. I had it correct. I almost thought I had an error there. So that's why it is plus. If you solve for FGD in terms of HY, again, you'll notice it is a negative quantity, which means our assumption of tension was incorrect. So that is in fact in compression. If you did one FEG, you could get it easily just by summing all forces in the x direction, but you're actually not asked for that in this particular problem.